Welcome to a lesson with Dr. Powell. Let's suppose that we're searching for x-intercepts or zeros of a polynomial. We have a list and we're trying to narrow down from that list which ones we should try out and pick from. So we have what's called the upper bound theorem that can help us. We want to be able to cross off potential zeros that are too high or too large. So taking a look at this is what we have. We know that if we look at the constant term and the leading coefficient here, our list actually comes from factors of 12 divided by factors of 2. So the largest we could maybe potentially try is 12. We know that already, and maybe the smallest is -12. The interim, we have factors of 12 to work with, and those divided by 2. Now, what if along the way, let's pick somewhere in the middle of, let's just look at what's positive. Let's just look at the positive part, and that's where the upper bound theorem comes into play. It focuses on where in this list we can cut things off and not look at. That's above a certain position for positive x-intercepts. So let's pick maybe 4, and let's just try 4 out. Now, as we're trying this, we can use the synthetic division machine to plug 4 into this function. It's like we're dividing the function by x minus 4. So we plug in, so we put 4 right here. Now we list out the coefficients, -12, or -2, sorry. -2, 7, 5, -28, and 12. Always making sure that we're not skipping any powers, because if we do, we need to put in a 0 as a placeholder for place value, as you would with working with base 10 arithmetic. Here we drop -2, get -8. We add, we get -1, we get -4, we get 1, okay, we get 4, we get -24, and we have kind of a negative large number. You could say it's actually -96. And then you add and you get -84. Now, if you take a look at this list, notice how we're getting lots of negatives. Like lots of things are the same sign. That should kind of tell us that maybe if we go higher, this pattern of having lots of negatives will continue. In fact, if we went a little higher, the next possible option is 6 here for factors. And if we tried that, let's see what happens. -2, 7, 5, -28, 12. So we get -2, we get -12, get -5, -30, -25, -150. It just keeps on getting bigger and very big. So negative big, and this is also a negative big. Notice that along the way, you have lots of negatives. In fact, all of them are negative. In fact, this theorem says that if you come across the fact that if all of them have the exact same sign, that means you're too high. And anything higher is going to be too high. We already checked 4, and we kind of had a sense that maybe this was getting too high because we only had one thing that was positive. And so we can kind of rule everything else out here as we go. Now, part of that is, so even just up here, we don't want to even, we don't want to pick anything higher than 6. We just want to go down lower now here and stay down here as we try things out. Part of this is if these things keep on getting negative, look at the process. you're multiplying this number to it, and it gets bigger and becomes more negative and more negative and more negative. If all of these stay the same sign, then what really seems to be happening is all of these are also getting larger in absolute value and larger away from zero, which means if your goal is to get a zero right here, it's not going to happen if all of these have the same sign. You can also think about this in terms of Descartes' rule of signs. For instance, let's rewrite this polynomial in terms of its quotient and its divisor and its remainder. Using this as the quotient, let's write that out. That's negative 2x. Now the power goes down, so cubed minus 5x squared minus 25x minus 178. We've multiplied that by the divisor x minus 6. And we added to that the remainder, negative big. Notice that when x is larger than 6, this guy is positive, meaning that the rest of this is negative and this is negative. So you can kind of in your mind just imagine this being replaced by some positive number, and just kind of looking at this, there are no sign changes. So in other words, there are no x-intercepts out there as long as this right here is positive, meaning x is larger than 6. Hence, Descartes' rule of signs can kind of be thought of a little bit in order to get this upper bound theorem in kind of blocking a place out via a division process, looking at the quotient here. And synthetic division is precisely a good way to go. So if we get all the signs down here looking the exact same, if they're all positive or all negative, then we know for sure we have gone too far and we can rule off everything above it. So let's look at one more quick example of that. Okay, so let's look at this one right here, and let's try some things out. So we know that we are going to be checking factors of this divided by factors of 1. Well, so the largest we could go is maybe 8, but maybe we can rule some things out a little bit. Why don't we look at, in fact, let's just try 4 for a minute. 4, and let's just get our coefficients. 1, negative 2, negative 4, and 8. All right. So we got 1, 4. Okay, we get 2, 8, 4, 16, and we get 24. Notice how all of these are positives. That means we've gone too far. And that means we don't have to try out 8, because 4 and anything above it is just too large to try. So this technique of seeing if all the powers are all the coefficients have the same sign is called the upper bound theorem, and it works for investigating positive x-intercepts and narrowing down where to look on our list. Thanks for watching.